Hello, we are Project Group 46 and our topic for today's presentation is 5G Wide Area Cellular Network. So, introduction, background of 5G development. The newest version of cellular network, known as fifth generation wireless technology, aims to outperform its predecessor in terms of data transfer rate, latency, and network capacity. It is based on a new radio technology called as New Radio, which operates on both sub 6 gigahertz and millimeter wave frequency. It is a replacement of 4G long term evolution, the Internet of Things, and the coming applications such as driverless vehicles, smart cities, virtual reality, and linked gadgets depends on higher data transfer rates and network capacity of fifth generation technology. 5G's disease latency also makes real time communication and quicker reaction time possible, which is crucial for applications like gaming, industrial automation, and remote surgery. 5G technology is anticipated to have a big impact on society and the economy. In addition to its technical advantages, it has the ability to significantly boost economic growth by opening up new business opportunities, generating employments, and raising productivity. Let's move on to the evolutions from 1G to 5G. So 1G came out in 1970 and 1980. It is used analog technology similar to landline phones. However, it has a lot of problems. The battery didn't last long, the sound quality wasn't great, and calls often get cut off. Plus, the maximum achievable speed was 2.4 kbps. 2G introduced digital technologies in 1991. This new system discussed concepts like code division, multiple access, and global system for mobile. In 2G, data could be transmitted at a maximum speed of 1 megabits per second. As technology progressed from 2G GSM network to the 3G Universal Mobile Telecommunication System framework, user experienced faster system speeds and quicker downloads rate, enabling seamless video call. 3G marked the advent of mobile broadband systems offering not only voice but also multimedia services. The underlying technology powering 3G was high speed packet access. Additionally, 3G leveraged multiple input, multiple output technology to enhance the power of wireless network and employ packet switching for rapid data transmission. Around 2010, the fourth generation mobile communication emerged with LTE technology. The LTE built upon the advancement of HSPA, offering higher efficiencies and an improved mobile broadband experience with faster data rates and reduced latency. This was achieved through OFDM based transmission technology, enabling wider bandwidth and advanced multi antenna system. This unified the world under a single global mobile communication technology. Now, wireless communication has entered the fifth generation era, characterized by an radio access technology. 5G not only enhance mobile broadband beyond 4G but also extend mobile communications to address various new use cases. We'll move on to 5G technology and its overall architecture. So the component of 5G system mirror those of previous generation, encompassing a user equipment consisting of a mobile station and an USIM alongside the radio access network and the core network as depicted in the illustration. The main entity of the NGRN is the GNB, where G stands for 5G and NB for Node B, which is the name inherited from 3G onwards to refer to the radio transmitter. The radio interface is named NRUU for similar reasons, although with diversions. Here, 5G is indicated by NR for new radio, and U is also a name inherited from previous generation. The GNB may be further split into GNB central units and one or more GNB distributed units, linked by an F1 interface. The 5GC is represented by the AMF UPF entity, the user plane function handling the user data, and in the signaling plane, the access and mobile management function, AMF, that accesses the UE and the RAN. Next is deploying 5G. There are two implementation of 5G. Initially starts with non-standalone architecture, which relies heavily on the existing 4G infrastructure. Due to this fact, early 5G network offered eMBB. Later 2020 onwards, standalone 5G networks started to become operational, and with this approach, a true end-to-end 5G network was utilized. In non-standalone mode, the 4G network manages the control plane, while the 5G NR network handles the user plane. In contrast, in the standalone mode, both the control and the user plane rely solely on the 5G NR network. Now, there are three components in 5G standalone setup: 5G NR, the next generation radio access network, and 5G core network. So, the 5G NR radio is the standard for air interface communication in 5G network. It represents a significant advancement over previous generations of wireless technology, providing enhanced speed, capacity, and latency performance. The next generation radio access network is the access network that provides the wireless connectivity between the user equipment and the 5G core network. The network consists of a sets of radio-based station connects connected to the core. The GNB incorporate three functional modules: centralized unit, distributed unit, and radio unit. The decisions on where to place the 5G RAN and core network function depends on the service requirements, the transport, and the compute capabilities deployed in the network. 5G RAN introduced new physical topologies, more functional split options, and low latency service, which demand shorter distance between user and computer. Network devices for 5G can be simplified by having one network that can provide ultra reliability and ultra low latencies to handle the needs of front haul, mid haul, back haul, and the core. Next, we'll discuss about 5G core network, which serve as the central hub of 5G communication, offering secure and dependable connectivity to this internet and facilitating access to various network services. It encompasses a multitude of vital functions crucial for mobile networking, including mobile management, subscriber data management, authorization, authentication, and policy management. This core network is entirely software based and designed to operate natively in the cloud, providing heightened deployment agility and leveraging cloud like infrastructure flexibility. Crafted by industry experts to meet the demand of 5G networking, the 5G core network adheres to the 3GPP standard, known as the 5G core, empowering it with the capability to govern and oversee network operations effectively. The user plane function comprises the user plane function, which acts as an intermediary between the radio access network and external networks like the internet. Executed encompasses various tasks such as routing and forwarding packet, examining packet content, managing quality of service parameters, filtering packets, and monitoring traffic. Additionally, the UPF functions as a pivotal point for mobility between different radio access technologies, which, when required, the control plane function encompasses various components. The session management function SMF is responsible for tasks such as allocating IP addresses to devices, enforcing policy controls, and managing sessions. The access and mobility management function AMF oversees control signaling between the core network and device, ensures security for user data, manages idle state mobility, and handles authentication. The non-access stratum NAS, which operates between the core network and device, is distinct from the access stratum AS, which manages functionality between devices and the radio access network. Furthermore, the core network includes additional functionalities such as the policy control function PCF for managing policies rules, the unified data management UDM for authentication credentials and access authorization, the network exposure function NEF, the NR repository function NRF, the authentication server function AUSF for authentication, the network slice selection function NSSF for selecting the slice serving the device, the unified data repository UDR, and the application function AF for influencing traffic routing and interacting with policy control. Next is the network slicing, which involves dividing a physical network into multiple virtual networks, each tailored and optimized for specific applications or subscribers. By utilizing cloud computing and virtualization technologies, resources of this underlying physical network can be dynamically allocated to this virtual slice based on changing user needs. A 5G network slice comprises a set of network functions and configuration tailored for a particular user case, potentially spanning radio access network, core network deployed on distributed cloud infrastructure, and transport network supporting flexible virtual function placement. The primary objective of 5G network slice design is to offer customized functionalities required for handling traffic specifics to each use case, while also providing a virtualized end-to-end environment that can be open to third parties, distinguishes it from the network sharing. Some of the key enablers of network splicing are wireless network virtualization, software defined networking, and network function virtualization. So, wireless network virtualization is basically virtualization has five methods: radio spectrum sharing, infrastructure sharing, network slicing by service, user, or application, abstraction layer definition that make it easier to access wireless network from heterogeneous network, and wireless network programmability and management to accomplish RAN slicing and network sharing in particular. Virtual networks are used to achieve wireless virtualization, which is made possible by virtualization. Next is the software defined networking plays a crucial role as it decouples the control plane and the data plane, resulting in the allocation of specific network modules to serve as a SDN controller. This separations allow for greater flexibility, which is essential for achieving effective RAN slicing implementation. By strategically implementing SDN towards the virtual wireless network slicing, it has the potential to simplify the management and programmability of such slices, mitigating potential complexities that may arise. Next is network function virtualization, which advocates for transferring network functions from dedicated physical network hardware to operates on virtualization platform environment deployed anywhere within the network. This facilitates the separation of network functions from proprietary network devices, enabling them to run on decentralized and virtualized network servers that can be deployed as needed, aligning with network requirements and service.
New radio. 5G new radio is a standard for air interface communication in 5G network. As the LTE evolves, there is a need to meet the increasing demands for some specific use cases such as ultra reliable low latency communication or massive machine type communication. In response to this, the third generation partnership project 3GPP has started on the new radio. New radio introduces a design that focuses on enhancing energy performance and minimizing interference. It is designed to be forward compatible with the future radio design development. 5G new radio is also engineered to expand the network efficiently over the next 10 to 15 years. 5G new radio employs many advanced technology in order to achieve the expected performance. Now we shall look at some of the main enabling technology. First, 5G spectrum. It targets three main spectrum ranges: 1 to 3 GHz for traditional mobile bands, 3 to 6 GHz for emerging mobile bands, and above 6 GHz for CM wave and MM wave bands. The MM wave above 24 GHz offers a wider bandwidth, fast data transmission rate that is used in many applications such as VR, AR, or high definition video streaming. Next, Massive MIMO is another crucial technology for 5G. Unlike the traditional devices with limited transmit and receive channels, Massive MIMO devices can have up to 32 to 64 TRX channels with up to 512 or more antenna elements. Massive MIMO enables multiple users under the same base station to share time and frequency resource. Hence, with Massive MIMO, the system has bigger capacity and also can boost the network with a lower density of base stations. Next, for the beamforming, it is used to identify the most optimal route for the data delivery to users. It is widely used in the mmWave communication system. It can overcome the path loss and interference, provides more reliable connection by enabling directional transmission and reception. In addition, 5G new radio introduces multi-connectivity for simultaneous use of multiple communication paths, which means connecting to multiple base stations or cells in the 5G network. This allows the UE to access radio resources from different nodes, meeting requirements for many applications. Lastly, the 5G new radio network has great flexibility. The physical layer is designed with purpose to adapt to different scenarios. Virtualization, which is enabled by network slicing, allows the virtual network creation, improve in resource planning, usage, and scalability. Now, we shall look into more detail of the 5G protocol stack. So in 5G, we have the user plane and control plane. User plane is to communicate between the user equipment UE and the base station, while for the control plane, the 5G protocol is to communicate between the user equipment, base station, and core network. The UE module at the user plane consists of 5 layers: service data application, packet data convergence protocol, radio link control, medium access control, and physical layer. For the UE at the control plane, it has the last 4 layers, and on top of that, it has a radio resource control and non-access stratum layers. Let's look into each layer. Service data application layer is a layer at the top of the 5G protocol stack for UE in the user plane. The role of this layer is to handle qualities of service. Radio resource control layer exists in the UE for the control plane and is responsible for the establishment, maintenance, and release of radio connection. Non-access stratum layer exists in the UE for the control plane and is responsible for mobility management, session management, network access control, security authentication. Next, the Package Data Conversion Protocol is responsible for handling the IP header compression and ensuring a secure end-to-end transmission of data in the user plane. This includes encryption and integrity check. The radio link control layer is responsible for providing communication between the UE and the base station. This layer is similar to transportation layer in the Internet Protocol. Medium access control layer is a layer that manages the access of devices to the shared resources within the wireless network. Last but not least is a physical layer. This layer is the lowest layer in the 5G protocol stack. It is tasked to transmit and receive data over the wireless communication. In this layer, technologies such as advanced antenna, massive MIMO, beamforming, and modulation and channel coding are used. Now, let's get into more detail of the physical layer. The physical layer is a crucial part of the 5G new radio specification, focusing on physical transportation of data. So 3GPP has released the technical specification series for the 5G physical layer as seen in the table below, and the relation between the technical specification can be seen in the figure next to it. About the physical channels in 5G, so 5G physical layer consists of three main models: uplink, downlink, and sidelink. The uplink model has the physical uplink shared channel, PUSCH, which is to transmit data from device to base station. Uplink model also includes the random access channel, PRACH, which consists of cycle prefix, preamble, and guard time during which nothing is transmitted. For the downlink model, it includes a physical downlink shared channel. It also includes a physical broadcast channel and paging channel. For the sidelink model, it includes the sidelink shared channel to facilitate the communication between devices with one another within the cellular network. So for multiplexing and modulation, for the downlink, the cyclic prefix OFDM is used. For uplink, both cyclic prefix OFDM and DTF as OFDM are used. The CP OFDM is used for scenario require high throughput, whereas the DTSS OFDM is optimized for environments with power limitation. So CP OFDM is actually an improvement from existing OFDM. The cyclic prefix symbols are placed to guard the interval between two OFDM symbols to eliminate the inter-symbol interference. So the figure shows the example of cyclical appending of tail symbol for CPOFDM. The modulation schemes used for downlink are QPSK, 16QAM, 64QAM, and 256QAM. For uplink, the modulation schemes used are QPSK, 16QAM, 64QAM, 256QAM for the CPOFDM, pi over 2 PPSK, QPSK, 16QAM, 64QAM, 256QAM for the DTF SOFDM with CP. For channel coding, 5G channel coding includes low density parity check LDPC for data channels and polar coding for control channel. Let's take a look in detail for LDPC. So LDPC codes are the type of error correction method for sending data. Based on the TS38.212, it is used because of the low latency, high throughput, low complexity, and rate compatibility. In the TS38.212, LDPC is defined with two base graph and 8 set of parity check matches for each base graph. So depend on the size of the data block or the data rate threshold, the graph 1 or graph 2 will be chosen. LDPC encoding involves the parity check matrix using the below formula, whereas input C and generated n plus 2 ZC minus K minus 1 parity bits W, where K is the number of bits to encode. ZC is taken as a minimal value of lifting sizes for LDPC and is determined based on ZC. To understand the process better, we can take a look at these two diagrams, which is for downlink and uplink communication. So in the case of downlink communication, the diagram shows the physical downlink shared channel. CRC is appended to the code blocks for error checking. Followed by this, low density parity check is also appended for further detecting error. Code words then go through rate matching, code block concatenation, scrambling, then QPSK modulation to generate complex data symbols before data transmission. Upon reception of the data at the 5G physical layer, decoding is done before passing data to another layer. For uplink, it is similar to downlink, but additionally, it incorporates the modulation scheme pi over 2 BPSK modulation alongside those that used in the physical downlink shared channel. Moreover, the physical uplink shared channel processing, there is an optional step called transform precoding, which occurs post-layer mapping. Now we shall look into some other key configuration and technology in physical layer. For bandwidth, each component carrier can have maximum bandwidth of 400 MHz and accommodate up to 3,300 subcarriers with the number of component carrier capped at 16 to ensure the efficient utilization of resources. For subcarrier spacing, it is derived from the fundamental 15 kHz subcarrier spacing in LTE. The selection of cyclic prefix lengths is adjusted accordingly. The table below shows the selection of cyclic prefix based on the subcarrier spacing, where the numerology mu equal to 0 represent 15 kHz. For data frame, each frame has a duration of 10 milliseconds. Subframe will have period of 1 millisecond. For slots, each typically consists of 14 OFDM symbols and serve as a single scheduling unit. The length of each slot varies according to subcarrier spacing, which with the slot length calculated as 1 ms divided by 2 to the power of mu. Mini slots are also supported to achieve low latency in data transmission. Mini slots support 2, 4, or 7 OFDM symbols. And lastly, beam management. So beam management is important for wave communication. The beam management is a process that establishes and maintains communication between the UE and base station. It includes acquiring and maintaining a set of transmit or receiving points and UE beams used for either downlink or uplink transmission or reception. So we have beam determination is to select which TXRX beams. Beam measurement is to measure the characteristic of received beamformed signals. Beam reporting is to report information of signals based on the beam measurement. And beam sweeping is to cover the spectral area. Now, after all the technology that 5G can offer, we shall look at the application and the solution that 5G can provide to today's world. The application of 5G technology in socio-economic context is divided into three main sections: enhanced mobile broadband (EMBB), massive machine type communication (MMTC), and ultra reliable low latency communication (URLLC). The EMBB offers up to 10 gigabit per second for uplink and 20 gigabit per second for downlink. It supports high mobility with speed up to 500 km per hour. This allows users to have better experience in applications such as high definition video streaming, AR or VR. Next, the MMTC involves the connection of massive number of low energy devices with minimal data requirement on large scale. With a 5G enabled, MMTC offers connection density up to 1 million devices per kilometer square, with the data rate from 1 to 100 kbps. Some examples include smart city autonomous device or vehicle. Lastly, the URLLC is an application that includes the mission critical control. The latency will be kept low, reliability will be ensured 99.999%, and mobility interruption time reduced to 0. The example of application can be seen under the National Public Security System or remote control. Some of the real-life example including the manufacturing. So many manufacturer employs the IoT sensors to monitor and control and get better insight of their machine and the production. With the 5G, this connection can be enhanced, lower latency with reduced error rate. Example of company exploring the private 5G technology is Huawei Mobile, Volkswagen Automotive, Zone 3 Agriculture Producer. Another example is the smart city. 5G is used for monitoring public utilities and overseeing city infrastructure, road congestion monitoring with a real-time high-definition traffic camera, which can be enabled by the 5G system. So, example is Singapore with the upgrade of 5G infrastructure for the whole country-wide usage, Planway for autonomous vehicles, and real-time toll rate system that monitor traffic congestion and manage traffic flow. As the world is moving towards the 5G, we are facing number of challenges. One of the challenge is the deployment of the 5G. Both standalone and non-standalone system will need some modification in the infrastructure, including hardware and software. The infrastructure requirement for the deployment of 5G will be intensive and expensive. Other costs involved are the purchasing of spectrum, testing, maintenance, and manage the 5G network. Replacement of the device that do not support 5G might be needed as well, which incur in extra money spent and inconvenience. Another concern is the network security. For the non-standalone system, the pre-existing issue in the current 4G LTE system might affect the new system security as well. Physical attack at the cellular tower, beamforming, small cells, and cellular device can happen, and this one are all the component under 5G. Now, I will pass my time to my partner to continue. Thank you.
Okay, next we'll move on to the future of wide area cellular network. Improvement in current 5G networks are crucial for addressing existing limitations and realizing the full potential of this technology. Firstly, enhancing coverage and reliability remains a priority. Additionally, reducing latency further is essential for applications requiring real time interaction. Increasing network efficiency and spectral utilization to accommodate the growing number of connected devices in data intensive service is imperative. Moreover, ensuring security and privacy in 5G network against emerging threat is critical, requiring robust authentication and encryption mechanism. Furthermore, advancement in energy efficiencies are essential to mitigate the environment impact of cellular infrastructures and extend battery life for mobile device. Finally, fostering interoperability and standardization across different 5G deployment globally will facilitate seamless roaming and interoperability, unlocking the full potentials of a connected world. Addressing these improvement areas will propel 5G network toward greater reliability, efficiency, and inclusivity, enabling transformative applications and services across diverse sectors. Then 5G Advanced represent the next phase in the evolution of 5G technology, aiming to enhance the capabilities of existing 5G network to meet the growing demand of users and industries. It built upon the foundation laid by initial 5G deployment, focusing on improving data rates, reducing latencies, and increasing network reliability and efficiency. One of the key objectives of 5G Advanced is to deliver even faster data speeds and higher throughput. Additionally, 5G Advanced prioritizes ultra low latency to support real time applications. Moreover, the deployment of network slicing enables operators to tailor network resource to specific use case, enhancing flexibility and efficiency. Overall, 5G Advanced aims to provide a more seamless and reliable connectivity experience while paving the way for transformative innovations across various sectors. Next, the journey from 5G advanced to 6G involves a progressive evolution marked by technological advancements and paradigm shift in wireless communication. Building upon the foundation laid by 5G, researchers and industry stakeholders are exploring new frontiers such as terahertz communication, massive MIMO, and quantum communication to unlock unprecedented levels of speed, reliability, and security. Artificial intelligence and machine learning will play a pivotal role in optimizing network management and resource allocation, while sustainability and energy efficiency remains key consideration. The transition to 6G also entails global collaborations and standardization effort to ensure interoperability and harmonized deployment across diverse ecosystems. Conclusion, 5G technology marks an important milestone in the evolution of wide area cellular network, offering transformative advantages and application for today's world. With the improvement in data spread capacity and connectivity, 5G technology can hope to revolutionize many industrial sectors from healthcare to manufacturing and entertainment. The technical aspect of 5G, including core network and new radio technologies, are the key point to achieve the network efficiency and robustness. As 5G continue to expand globally, there are more applications being innovated under the categories of enhanced mobile broadband, massive machine type communication, and ultra reliable low latency communication. This application cha- this application enhance our quality of life and industrial productivity. Looking ahead, the future of 5G and wide area cellular networks are promising, with ongoing developments in 6G on the way to unlock new possibilities. Thank you.